Hi guys, in this video we're going to have a look at scalars and vectors. We're going to be defining what scalars and vectors are, and we're going to be seeing how we can do algebra with both scalars and vectors. But before we have a look at that, we're going to have a look at this concept of Euclidean space. Now, Euclidean space is basically our familiar 3D space around us. So say we've got like a field thing, we've got some hills there in the background. So we've got our field going on right here, and I'm kind of drawing it in kind of a 3D style right here. But basically, Euclidean space is just the space all around us, and we can represent it by a suitable set of coordinates. Now, most of the time, we like to choose the X, Y, and Z coordinates for representing any point in 3D space. And we typically say that this is the x-axis, so the horizontal axis is the x-axis. This right here is the y-axis, and this right here is the z-axis. Now, of course, it could be, this is entirely arbitrary. It could be any direction at all. But we're just choosing this set for convenience. So this is basically 3D space. We represent it by an x coordinate, a y coordinate, and a z coordinate. Now, all physical quantities, so say like, work or energy or distance or velocity, have either just a magnitude, for instance, temperature. Temperature is just a quantity that has a magnitude, or it has both a magnitude and a direction. So say like a force. So a force is, a quantity which has a magnitude and a direction. Quantities with just a magnitude are called scalars, and they have just a magnitude. So some examples of this include length, speed, energy, and power. So those are some examples of simple scalars. They only have a magnitude, they don't have an associated direction. However, quantities like force, which have both a magnitude and a direction, are called vectors, and they have both a magnitude and a direction. Now, the thing about a vector is that it's actually, mathematically speaking, it's a different type of quantity to a scalar. A scalar is simply something which has a number. However, a vector, we actually have to treat slightly differently mathematically, and we'll see how we denote vectors as opposed to scalars in just a second. But some examples of vectors include displacement, velocity, momentum, force, alongside many others, which we're going to have a look at in future videos. Now, a side note, a scalar and a vector are actually a specific case of a tensor. Now, a tensor is basically a mathematical object. Now, how do we distinguish between vectors and scalars typically? Well, scalars, say we'll take a scalar like temperature. I could just write the symbol T, or we take another scalar like energy, we just write the little symbol E, or power, just, lowercase p. We just simply denote them like that. Typically, vectors we denote slightly differently, and we do this to show that they're actually a different mathematical type of object. With displacement, we actually use the symbol r, but what typically you do if you're writing it down is put a little arrow on it, or you could underline it like that. Now, in some textbooks, you'll probably see the vectors denoted in a bold format. Of course, it's a little bit harder to do that if you're handwriting it. So what I tend to do is I tend to do the little arrow on top to denote a vector. Now, the first vector we're going to have a look at is in fact this r right here. And going back to what I was saying earlier about Euclidean space, we can actually represent any point on Euclidean space with a vector, and we call this a position vector. But in order for this to work, we have to define where our origin is. We need to know where the 0 point is. Otherwise, we don't know what value to choose r. So here's our little origin, and let's draw a set of axes. So this is the z-axis right here. This is the y-axis, and this is the x-axis. And we can take any point in this space right here, any point we like. So say we choose this point up here, for instance, we can break this point down into three components, three set of coordinates, and the position vector gives us the value of each of the three components. So say this point up here is something like, it has an x coordinate of 4, has a y coordinate of 3, and it has a z coordinate of 2 or something, then its position vector, it has a position vector associated with it at that point of r, and that equals 4 in the x hat direction plus 3 in the y hat direction and 2 in the z hat direction. Now, what are these funny little things I've introduced right here? Well, those right there, these guys are the unit vectors that correspond to our coordinate system right here. So this x hat right here is, in itself, it's actually a vector, but its purpose, all it does is to point in that particular direction. It doesn't have a magnitude of itself. All it has is a direction associated. So remember what I said about vectors having both a magnitude and a direction. It has a magnitude of just 1, but the point of it is that it points in the x direction. Similarly for the y hat, that's got a magnitude of 1 as well, and it points up in the y direction, or that way actually, as I've defined it. And the z hat again has a magnitude of 1, but it points in that direction. So that is what we call a position vector. It's a combination of these three unit vectors. So to get to this point 4, 3, 2, we have to go 4 units in the x direction, 3 units in the y direction, and 2 units in the z direction. And this is how we denote any position in Euclidean space. We denote it with 3 coordinates. So how exactly do we handle vectors? Well, as I said, the vector can be broken down into 3 different coordinates. So in the last example, I used 4x hat, 3y hat, and 2z hat. But more generally, we can say that it's some certain value in the x hat direction plus a certain value in the y hat direction plus a certain value in the z hat direction. And so these 3 numbers, these are just actually scalars right here, but these little unit vectors here, they're actually vectors themselves. But of course, 4, it's just a number, so it's just the factor that you need to multiply each component by in order to get, the total vector right here. So how do we exactly represent a vector in itself? Well, we normally just represent it by an arrow right here, and you've probably seen this before, but a vector is typically represented by just an arrow, and we normally just put the little label on right there. But of course, this arrow right here, we can break it down into its constituent parts, like here. So what we can actually do is we can resolve the vector. This is what it's called. It's called resolving the vector. We can resolve it into its various different coordinate systems. And for this example, I'm just going to look at the 2D case. I'm going to drop the z term. So now I'm defining this axis to be the y-axis and this axis to be the x-axis. So I'm now taking the 2D case just for this particular example. So we can resolve this vector r into where its components parallel to the y direction, and its component parallel to the x direction. So again, this is basically exactly the same vector, except I've dropped this term right here, just for simplicity. So again, we can say that r equals rx in the x hat plus ry in the y hat. And just a quick note, you might sometimes, instead of seeing x hat, y hat, and z hat, you may see I hat, j hat, and k hat. I'm going to be using x hat, y hat, and z hat because I think it's a bit more clear as to what it is. Plus, I think most people are probably more used to x, y, and z being the typical Cartesian coordinate system. So I'm going to be using x hat and y hat and z hat. Now, all vectors have a magnitude and a direction, and the magnitude of the vector is in fact just a scalar itself, just if you just have the magnitude. And we normally just denote the magnitude of any vector as simply r, so there's no longer an arrow above it. And the magnitude we typically put with two straight brackets in front of it. And the magnitude of the vector in this case is simply the length. So say this point up here had coordinates of 3, 2. So what the magnitude of the vector is it actually is the distance from the origin right here to this point 3, 2. And how do we work out what this distance is? Well, we simply use Pythagoras, of course. We use a squared plus b squared equals c squared. Of course, it's simple Pythagoras. So we know that this length right here must be 3 because it has an x coordinate of 3, so it's 3 along the x-axis, and it has a y coordinate of 2, so therefore it has this length up here is 2. So how do we work out what this length is here? Well, it's simply the square root of 3 squared plus 2 squared, which in this case is the square root of 13. That is the magnitude of this vector here. Now, the direction of the vector, we have to be a little bit more careful because we have to define where the 0 point is. Much like for our Cartesian coordinate system, we have to define where the 0 point is. And typically, we define the direction as being the angle from the x-axis. So it's the angle between this vector here and the x-axis right here. And typically we use theta to represent the angle. To work out theta from the things that we know, we need to use the tangent function. And so from here we can see that tan of theta equals 2/3. And so theta in this case equals arctangent of 2/3, which is 33.7 degrees or 0.59 radians. So that's how we calculate the magnitude and direction of any vector. So more generally, we can say that the magnitude of r is simply equal to the square root of its components squared, because that's what we did. We took the x component, which just happened to be 3 in this case, and the y component, and then we added them in what we call quadrature. So we added the squares and then square rooted the result. So it's the x component squared plus the y component squared gives the magnitude. Now, this is of course the 2D case. In 3D, it's actually very simple. What we have to do, it's not much harder at all. We just do the x component squared plus the y component squared plus the z component squared. So all we have to do is just add on the z component, and then that gives us the magnitude. Now for the angle, what do we do right here? So we can say that tan of theta equals the y component, which was the vertical, over the horizontal, which is the x. And so rearranging, we simply find that theta is arctan of ry over rx. So that is how we calculate the magnitude and direction of any vector. So now what I want to do is I want to redraw this diagram we've got right here. So here's our axes. So we've got the y-axis going up here, the x-axis going along right here. There's our origin, which I'll mark as O. And here is our vector. And it has this actual side length is r, but I'm going to use the scalar. This is actually just denoting the length, and of course we have the x component here and the y component going along here. And so what we said before was that to find r is just the magnitude of the vector, and we just have to add up the components and square them and add them, and then take the square root. And we also said that this angle right here was theta, and that is the angle between the x-axis and the vector itself. So from this diagram, we can actually say that the x component of this vector is simply this length right here multiplied by the cosine of this angle right here. And that's simply, using the fact that adjacent over hypotenuse is the angle, but so cos of theta is adjacent over hypotenuse, so we simply bring the r up, and then we get rx in terms of r and theta. And similarly, of course, for the y component, it would be equal to r. However, this time it would be the sine of theta, because of course that's opposite over hypotenuse. Sine of theta is ry over r. Bring the r up along the other side, and then you simply get ry equals r sine theta. So this is a good way to obtain, kind of do the opposite almost, to obtain the components if you know the magnitude and the angle, and you can obtain the components of the vector. So now let's have a look at scalar algebra. Now, we say that scalar addition is known as commutative. And what do I mean by that? I basically mean that, say we have two scalars, a plus b, we say that a plus b is exactly the same as b plus a. Might sound pretty obvious, but that's what's known as commutative. So it doesn't matter which order you add the scalars in, a plus b is always b plus a. Now it's also known as associative, and this is basically a plus b plus c is exactly the same as a plus b plus c. So if you add these two numbers first and then add that one on, it doesn't matter if you add that one first or whether you add those two first and then add that one on later. It doesn't matter which way around you do it, you'll still end up with the same result. And the last thing to note is that when you multiply a scalar by a scalar, you'll simply end up with another scalar. So we can just say that AB is C, and all three of those are scalars. Vector algebra behaves almost as you would expect, with a few slight things that you have to bear in mind. Components of a vector add together. So say we have one vector, so let's have a vector A, and that is 3x hat plus 4y hat. And we have another vector B, which is 2x hat plus 5y hat. We need to add the x hat components and the y hat components, but we have to do that separately. So we have A plus B equals 3x hat plus 4y hat plus 2x hat plus 5y hat. We've just simply added those two together. We've substituted A for that and B for that. And so we can simply see that we'll end up with 5x hat plus 9y hat. So you simply add the x hat components and you add the y hat components. Now, vector addition is also associative. So, if you add, doesn't matter which order you add add them in as long as you add the correct components together. It doesn't matter what order it is. And the last thing to note is that if you multiply a vector by a scalar, and we normally put the scalar before the vector, we'll end up with another vector. So a scalar b multiplied by a vector a is a vector c. So finally, let's do a practice question just to round off what we know. So say we have a vector a, and that is 3x hat plus 2y hat. And we have another vector b, which is 7x hat minus 4y hat. Then what is a plus b? Well, that's very similar to the example that we just did. So we simply have to add the x components and add the y components. And so all we have to do is add the x components. So 3x hat plus 7x hat is 10x hat. And then add the y components. This, of course, is negative, so we're going to have 2y hat minus 4y hat, which is minus 2y hat. So that is a plus b. That is the vector that is a plus b. Now, the next thing we want to ask is, what is the magnitude of this vector? Well, the magnitude, of course, is we simply have to take each of the components and square them, add them, and square root them. So it's simple Pythagoras. So we do square root, so we know that the magnitude of a plus b equals square root of 10 squared plus 2 squared. Then you're going to end up with square root of 100 plus 4, which is the square root of 104. And you could probably evaluate that to an actual number in your calculator. So I hope that gives you a good introduction to vectors and the difference between scalars and vectors, how you can do algebra, simple algebra with vectors. And in the next video, we're going to be having a look at multiplication of vectors. So see you guys then.